Okay, I think we'll go ahead and get started. Good morning. My name is Aaron Cutshall, and I am a healthcare solutions architect. And just make sure that everyone's in the right room. We're here to talk about whales, right? Or okay. Or really, we're going to talk about big data. I mean, you stop and think about what big data is. How many people work in big data? Let's show of hands. Just a few. How many people expect to be working in big data? A lot more. And how many people just don't raise their hands for any reason? Oh, okay, good. Just make sure everyone's awake. Now, as you can tell, you guys have already seen the slides, so we're going to turn off your phones and everything, so that way we don't get interrupted when we get those emergency calls. And if you haven't seen the slide also about what PASS has to offer, how many people are here for the first time? Excellent, great turnout. You enjoy it? All right. Yeah, this is a really wonderful event. How many people have been to a SQL Saturday? All right. So most of you, that's great. SQL Saturday is a great opportunity to also get some training as well. And so there's all sorts of events, virtual groups, et cetera, local groups. How many people are in a local group, local chapter? Only a few, okay. Take a look in the PASS website. There's probably a local chapter in your area. And if not, then you can probably do something about it by starting one. It's always a good way to get people together to learn. Session evaluations. I know this is always one of those things that a lot of people forget about, but I really appreciate it if you would let me know by doing the session evaluation, because it helps me to do a better job. And if you have something specific to comment on, I would appreciate that, because just looking at the numbers, it doesn't tell me as much as what the comments actually do. So I would appreciate that. So again, my name is Aaron Cutshall. Got some contact information there. I've been around for 30 plus years on working in healthcare for the last 11 years. 20 years before that, I was in manufacturing and warehousing systems. I'm the chapter leader for the Indianapolis PASS chapter called IndyPass. And been speaking at SQL Saturday events all across the country, everywhere from as far west as Portland, Oregon, and far east as Tampa, Florida. So I appreciate that.
There'll be whales here.
Okay. Yes, that was the obligatory Star Trek reference, so now that we got that out of the way. But really, I just wanted to bring the point that, when we talk about big data, it's always, like not just an elephant, but it's a whale. It's really, really huge at times. And so the question is, people think that, well, can SQL Server handle that? How many people are doing big data on SQL Server? One. Excellent. You can do big data on SQL Server, and we'll talk about that here. So first of all, we would ask the question, what is big data? How many people know what big data is, for sure? A few of you. I would bet that your definition and your definition of big data aren't the same. We're going to talk about some common myths as well. And also, we're going to go over a couple of case studies about big data that was implemented on MongoDB and another one on Hadoop, and to show how they went really wrong because they were using either the wrong tool or using it incorrectly. And so we're going to go over that with the observations. Then we'll talk about big data on SQL Server. How can you do big data on SQL Server? There's a project that I did called Core Analytics. We're going to go over that, and when we talk about volume of data. And then we're going to cover how you can set SQL Server up for success by organizing your data properly within table structures, how you handle your queries and your T-SQL coding and for your store procedures, and also indexes and partitions. We'll also discuss some alternate options that we could have done as well. Then we'll have a few closing thoughts at the end. So what is big data? Well, there are varying definitions of it. So let's look at a few. The Oxford English Dictionary said that big data is extremely large data sets that may be analyzed computationally to reveal patterns, trends, and associations, especially when relating to human behavior and interactions. Wow, that is a mouthful, isn't it? Well, what I did is I identified some keywords from that, such as large, analyze, patterns, trends, and associations. But it didn't really tell me what big data is. It tells me what is done with big data. Merriam-Webster dictionary said, it's an accumulation of data that is too large and complex for processing by traditional database management tools. So they're making the assumption that if it's big data, then you can't do it in a relational database. Not sure if that's a good definition. It doesn't seem like a definition to me. But I did pull out a few keywords there. Accumulation, large, and complex. So we're seeing kind of a trend here, right? Gartner research said it's a high volume, high velocity, and/or high variety information assets that demand cost-effective, innovative forms of information processing that enable enhanced insight, decision-making, and process automation. Wow, again, a mouthful. And really the first part of that is closer to a definition of big data, the high volume, high velocity, and high variety. And we're going to get back to those 3 V's later. But the rest of it, again, is talking about what is done with big data, not necessarily, again, what it is. And so here, again, are a few keywords that are pulled out of that. So with all that verbiage, I did get a few more. And then MIT, you think they would have the definition of it. And they said it's big data is a term describing the storage and analysis of large and/or complex data sets using a series of techniques including, but not limited to, NoSQL, MapReduce, and machine learning. Again, they're talking more about what is done with big data. But again, we come out with a few keywords such as storage, analysis, large, complex. Again, a recurring theme. But this gives the impression that relational database management systems can't handle large and complex data. How many people are familiar with Salesforce? Okay, they handle all of their data in SQL Server. They do not use Hadoop for that. And so again, large and complex data can be handled in a relational database system. So what is big data? So let's take a look at some reality. The definition of big data is really a moving target. Nobody really knows what it is, and it all depends upon your perspective. Berkeley University surveyed 40 industry thought leaders on what the definition of big data is. Not a single 2 of them could agree. No one agreed out of 40 thought leaders in the industry. So most people think they understand what big data is, but the question is their understanding is different. Everyone has a different definition that is skewed by their own perspective, how they look at it, what their needs are. Now, there are some characteristics of big data. I mentioned earlier about the 3 V's, volume, variety, and velocity. Some people also add 4 additional V's. Veracity, which means how can the data be confirmed? Variability in the types of data and in the speed at which it arrives. Visualization, I really don't see that as being part of the definition of the big data. That's more of what you do with the results afterwards. And then value. Of course, value is very subjective, and that depends upon who wants the results. It's just what the value is. But the biggest definitions come up on what the definition of structured or unstructured. There's huge disagreements on that. So how many people think that big data is all unstructured data? A few. Well, there is a difference between unstructured and non-discrete. Of course, if you take an MP3 file, you can play it on many different software packages, many different devices. Is that structured or unstructured? I'm sorry? You said unstructured? It is structured, because if it weren't structured, you wouldn't be able to play it on multiple different devices. Now, really what happens though is when people are looking for information that's in the MP3, such as the text of what someone is saying. So like, for example, we took a recording of this show, the audio recording, and we have that in an MP3 file, but we want to know what is the information in what I'm speaking, then that is non-discrete because you can't easily get to it. So the structure of it depends upon what you're looking for. If you're wanting to just play an audio file, it's highly structured. If you're wanting to get at the spoken information that's in it, then it's unstructured or indiscrete. So again, it's a matter of perspective. So let's take a look at some myths involving big data. Big data is a new phenomenon that came about only in recent years. How many people believe that? Good. There's hope for you yet. The genome database uses a relational database management system for mapping the human DNA, and that's been an ongoing project for decades. The astronomical data model, I mean, you're talking about astronomically large data sets. They've been doing it long before their PCs were around even. So that's big data. Another myth is that to process big data requires totally new platforms and new thought processes. You know, it's kind of like the old saying, you know, we're going to have to, you know, open up a new door and bring everything in. Well, a lot of that is marketing. And who reads those marketing articles? It's the CIOs, the CEOs, et cetera. And there's an implicit pressure on them that if you don't have big data, your business is not going to survive. Oh my gosh, we got to go do big data, whatever the heck that is, we got to go do it. And so that skews a lot of perception as well. Another myth is that because big data is so large, it can be difficult to process. Well, really what we're talking about is not the size of the data, it's we're talking about complexity. And again, complexity is due to how the data is organized. And so it's a myth that NoSQL platforms only NoSQL platforms can handle big data. Also, I should point out something I didn't earlier is that whenever you see these underlined green lines, when you get the slides, if you have access to those, they're links to these articles that I referenced for this. Another myth, NoSQL vendors and training companies promote these myths like Hobbes is the Calvin, Hadoop is the big data. So they're trying to make a knee-jerk reaction association in you so that when you think about big data, boom, Hadoop pops into mind. Big data applications require little or no performance tuning. How many people have heard that one? Yeah. And I'm sorry to say, but all data systems require tuning for proper performance. You can't take something just out of the box, turn it on, and then just go. Because then really what you're doing is you're taking plug and play concepts into plug and pray that it works. Analytics requires big data. How many people do analytics on small data sets? Of course. We do analytics on all sorts of things. You know, you don't have to have big data just to do analytics. And it's been performed for years in relational databases. Insurance companies, long before computers, had data scientists, and they called them actuaries, right? Another myth is that big data is only unstructured data. Well, again, we're talking about the difference between unstructured and non-discrete. When you load data into a relational database, you organize the data because you put it into tables with columns and rows. And so you know what that structure is. In NoSQL environments, while you may think of it as being unstructured, when you go to query the data, what do you have to do? You have to determine what the structure is so you know how to go pull the data. You have to know where to go to get certain pieces of data. So at some point, you have to apply structure to the data, whether you do it when you load it into the database as a relational database system, or when you put it into unstructured into a NoSQL environment, then you have to determine structure when you go to pull the data out. So at some point, you have to determine the structure of the data, whether it's before or after. Another thing is that big data is too big for SQL. Well, here they were referring to the language SQL. Well, all massively parallel processing platforms will support, because of their parallel processing, they support SQL. You know, anybody ever heard of Netezza or Teradata? You know, those are huge platforms. They have SQL environments, So yes, you can do big data and still use SQL. I find it interesting that after the big push of NoSQL, meaning that these database environments like Hadoop did not use SQL. That's why they got the moniker NoSQL. But what do you see on them now? Hive SQL, trying to put an SQL interface on it. Why? Because that's the language that most people who work with data understand. Now, they're not designed in the same way that a relational database is. They're not effective like SQL Server is because it's not built into the engine. It's an add-on, and it's meant for convenience, not for production use. So let's take a look at a scenario involving MongoDB. Now, being in healthcare, I work with clinical quality measures. And these are measures that look at how well patients are being cared for. In there, they determine what a denominator is, and this is what is to be measured. And then the numerator determines if the particular denominator passes or fails the measure. For example, if we're looking for diabetic patients, the denominator, who had a retinal eye exam in the last 12 months, that would be the numerator. Clinical data is also defined by taxonomies and terms. So we add some complexity to it. Taxonomies are like coding systems. For those of you in healthcare, like CPT and SNOMED, et cetera. And then the terms would be the values of those codes. And then when you're talking about the data per patient, it gets pretty extensive because then you're talking about encounters and medications and diagnoses and procedures and blah, blah, blah. And it gets pretty big and extensive. Now, in Mongo, this particular project, what they did is they had 40 clinical quality measures of varying complexity. Some of them were simple, some of them were more complex. And they had data for 750,000 patients. And this data was stored in XML documents, known as the clinical data architecture. And each document was one per patient, and it contained all the known data about that patient. And MongoDB is a document database. It's what it's designed for. So kudos to that point. They sharded the data across 10 servers because they wanted to get that parallel processing out there. And they use Ruby on Rails for their processing logic. Okay? And they were really pleased when they got their results generated in 8 hours. I thought that was kind of odd because I had a similar system, easy for me to say, right? Similar system on SQL Server. I had the same 40 clinical quality measures. I had data for 2.5 million patients, and I had it stored on my laptop. The data was normalized. I broke it out into elements and attributes, and I only loaded what was required for the measure calculations. I used T-SQL for my processing, and it was all, of course, set-based logic. And I had results generated in 45 minutes. They didn't believe me. Now, why is that? Well, the MongoDB version relied on procedural processing. Now, this could be because, there have been advances in Mongo since this occurred. This was probably about 5-6 years ago. But a lot of it was the way that they designed their system. The data in the XML documents, because they had it per patient, Mongo is not a relational database, and so it couldn't make a correlation from one patient to another. It couldn't search across the documents, and so it required examining each document for data for that measure. So it'd be like, look at document 1. Oh, does that have what I need? No. Look at the next one. Oh, yeah, it has. So let me set that aside. Let me look at the third one. And it just went through that way. Healthcare data really is highly structured, and it's relational. And there is a relationship between when you go to the hospital and you have diagnoses and you have procedures, et cetera, that's all related to your encounter. So in my SQL Server version, I focused only on the data that was needed. and I used set-based processing. After all, that's what SQL Server is really great at, isn't it? And I calculated each measure for all patients simultaneously. So I processed the measure only once and looked at across all the data for all patients. Let's take another look at one for Hadoop. Now, in this one, it actually it started on SQL Server and then went to Hadoop. This one is supposed to analyze claims for fraudulent payments and billing errors, et cetera. And the idea behind it is that you want to process this claim and pay it within 24 hours because of legal requirements. So you have a small, narrow window to look for problems in the data. And the claims analyst has to review those generated recommendations before they submit it. And if they can't get a recommendation, they have to go ahead and pay it. There were approximately 150 analytical concepts. Some of them were pretty simple, some of them were more complex. Each one of them looked at a different scenario for what would consist of a fraudulent or billing error, et cetera. And the results of that would generate, for each suspect claim, it would have one or more reference claims associated with it. So for example, if a person had cataract surgery in their right eye, and it would look through the history to see, well, did they have one in their right eye already? Because you only get it once per eye. On SQL Server, what they did was they copied the data from the claims processing server once per day after midnight. So there was time lost already. They waited until midnight to get the data. The data architecture that was used on the claims processing system was copied over as is. That data was set up for processing the claims, not for doing analytics on it. There were large records for the claim header, and for the detail was even larger, multiple columns, 80 plus columns. Most of the data was stored as text, including the primary and foreign keys were text. The what? Is it blinking out?
Yeah, maybe reset that real quick here.
Okay. See, no matter where you go, you're going to have technical difficulties. Yes.
Okay.
All right, cool. Okay, see, where were we? So they stored the data still in the original format that they had as text keys. Now, as most of you know, that's not optimal for analysis. It's not even optimal for most data processing to use text-based keys. They also had stored procedures for each of those 150 concepts. Now, unfortunately, they weren't developed by T-SQL developers. They were written by people who had no idea, really, how to do much beyond writing a few simple SQL queries. So you can imagine what the quality of those stored procedures were like. These guys did the best they could, but they should have had some help with it. And so the stored procedures were inconsistent, and they obviously weren't optimized for their logic. The procedures themselves took considerable time to execute. A few of them completed within an hour, but most of them took several hours, maybe up to 3 or 4 hours. There were even a few that could not run in the 24-hour time period. So therefore, they had to go ahead and pay those, and they could not realize any savings on it. So somebody got the bright idea. I know what, we can fix this by going to Hadoop. I read this article that said that Hadoop is much faster. So let's put it on Hadoop. One thing they did right was they changed how they captured the data. They captured it as a live feed from the claims processing system. Woohoo! Good points there. That was a good thing to do. However, they kept the data structure exactly the same as it was. They also kept the concept processing logic. They took the stored procedures and cut and pasted them into Hive SQL scripts. Oh, and by the way, since Hadoop doesn't really do updates and deletes, they had to write some code in there to work around those, which usually involved creating a new table, which is really a file, dropping the old one and renaming the new one to the old one. So that took even longer. Initially, they could only convert the simplest concepts because it took quite a long time for them to do that. And they did get some time savings, but we're talking about minutes, not the time savings they were looking for. And so they couldn't still get more than one execution per day. So why was this? Because the data architecture, again, was not optimized for analysis. The SQL Server procedures weren't optimized for performance because they weren't created by developers who understood the T-SQL language. And also, there was very little documentation on the purpose of those store procedures, the business logic. Basically, they had a vague description of what it should do, but not a reason why they were going through all these hoops in the code. Hadoop was chosen for its speed, yet SQL was used for the application interface. Again, the SQL interface on Hadoop is not designed for a production system in that sense. It's designed for convenience. And there we go, blinking again. So the choice is made without a proper analysis of the problem. No one really looked at the root cause of it. And had the resources and the money been applied to the original implementation, it could have been done a lot sooner and cost a lot less. But again, no one looked at the real problem. They thought, I know what, let's put it in Hadoop because that'll solve all of our problems. The platform was chosen to be the solution. It wasn't, there was no analysis again on that. And management picked the platform. It was handed down to the IT folks, said, you're going to do this on Hadoop because I read an article that says it's much better. It was also high visibility. So it had to be impressive. Using the newest and shiny tool is impressive, right? We're going to be the first ones on the block to implement this latest and greatest tool. And then also the thing that came back was that they thought they could save money because, you know, it's Hadoop. It's free, right? Free is free, isn't it? Yeah, well, there's a hidden cost to free, believe me. Again, no root cause analysis was done. They figured the problem must have been in the programming. And it didn't help that we had all-day meetings in an attempt to improve productivity. You know, it's kind of like Dilbert was in our office, and, you know, we had meetings to determine why we were having so many meetings. You know, so where's the logic in that one? Again, it was really about the wrong tool used for the job, or the tool was used incorrectly. So like my dad always said, don't use a screwdriver for a chisel. Just because you can sometimes doesn't mean you should. Okay, so we talked about what big data is. We covered some definitions and some of the common myths about it. And we talked about when big data goes bad, you know, with the MongoDB application and the Hadoop application. Anybody have any questions at this point? Wow, I did that great of a job?
Apparently you did.
All right, yes. Oh, you're just stretching. Oh, man. Here I thought we had, oh, there we go, there's a question.
It's a question of observation maybe, but
I'll take observations.
is there some sense that the attractiveness of these non-SQL things is because people don't want to take the time to learn how to normalize? They're trying to pick something that's simpler than SQL?
To answer your question, are people picking them because it seems to be a simple solution? Yes, I would say that is true. It is far easier to say, well, you know, let's try this quick and easy solution first and see if that solves all of our problems without really taking the time to analyze it and dig deep into it and see what the problem may be. Yes, you're right. Yes.
I've heard a lot of times it's used for analyzing logs and stuff like that, which is a lot more just text. It has formats, so I'm not going to say it's unstructured, but
Yeah.
you know, it's in these formats that can be hard to analyze in SQL.
Right. Now, don't get me wrong. Hadoop is a great tool. It really is, when used properly. You can do a lot of great and amazing things with it. Same with MongoDB. I've seen some awesome MongoDB implementations. So I'm not trying to put those tools down at all. All I'm trying to say is you want to use the right tool for the right job. Yes?
Explain the discrete and discrete.
Sure. So the definition between discrete and non-discrete is that, let's say when you're looking at a form, you're filling out a form, and there is a box that is for your Social Security number. That is discrete. It is labeled because you know that is specifically for your Social Security number, as opposed to scanning through a whole bunch of text looking for something that might kind of fit the format of a Social Security number. That's non-discrete. Make sense? Okay. All right, so what we have coming up next, we're going to talk about big data on SQL Server. We're going to talk about some table structures and partitioning, keys and indexes, querying large data volumes, and store procedure techniques. So first of all, here's the project that I worked with on. It's called Core Analytics. And again, it was for healthcare measures, clinical quality measures, as well as utilization measures. And utilizations was to determine how efficient that a hospital was doing, you know, as far as their cost or performance. We had clients that were for major healthcare provider systems. One hospital network had over 70 hospitals that we collected data for. And so we're talking about hundreds of millions of patients and their clinical data. We had over 20 clinical quality measures, about 10 utilization measures, and we were able to do the calculation for that in about 1 to 2 hours. So, big data on SQL Server, yes, it can be done. We also had, through this was a measure calculation engine. The measures were edited and created by non-programmers. There were clinicians that did this, and they were stored as XML documents. And these documents were then compiled into store procedures. So as you can imagine, the measure definitions were pretty regulated as far as the format and structure. The data was imported from the electronic health records or electronic medical record systems. And then we mapped the data into standardized taxonomies and terms. That way the measures could know what to look for. And we transformed them into a known data structure. Some systems try to be everything to everyone and allow this great flexibility. And that was, you know, a great kumbaya moment, but it didn't help to process the data electronically because you have to have it in some known structure. And so we transformed it into elements and attributes. An element would be like, you know, encounters and patients and diagnosis, et cetera. And attributes would be like their columns, you know, their additional characteristics. Now, we had 3 basic steps. We had our ETL, which really took up the most time of the process. And then we had our calculation, which is about 1 to 2 hours. And then we spent some time on preparing the results for analysis and reporting. Now, I will tell you, what I'm going to show you is this is not a treatise on SQL Server internals. There are a lot of people that are smarter than me on that subject. That's not what we're going to cover. This is not a set of step-by-step instructions. So I can't say that you're going to be able to take it back and use it as it is. And it's not a tome of DBA black magic. But what it is lessons learned from the trenches. And data architecture techniques, how you structure and organize your data. Some database programming techniques, so how you write your SQL store procedures. And it's a good starting point in the right direction. So let's start with our table structures. First of all, it is okay. In fact, I would suggest that it's more than okay to restructure your data for analysis. First of all, you shouldn't be doing your data analysis on your source system anyway. but you would put that onto a different system for its analysis, and you can restructure it to make that analysis better. You want the right level of normalization, but what that right level is pretty subjective. It depends on your application. So I can't give you any rules of thumb there, because you know what they say about rules of thumb? They're only applicable to thumbs, right? We want to minimize the data to essentials. So when you do your analysis, get rid of your extraneous data. That'll make it a lot easier. That way you can limit the number of tables that you have involved, and you want to limit the number and size of their columns. Table keys. I am a big believer in using surrogate keys, especially for analysis, because text keys take additional processing that will kill your performance. And absolutely, do not use GUIDs for your keys. How many people have a system where you found had GUIDs for your primary keys? I feel so sorry for you. I really do. Because GUIDs are by nature what? Random or pseudo-random. And so when you're using those primary keys, which most often happen to be clustered indexes, what happens to your clustered index when you're putting in random data? Yes, you get a lot of index fragmentation. You're having your system thrash for really nothing. So what I did is I also replaced text searches with numeric keys. So if I had, and I'll show you this later too, when we talk about how I got rid of some of the key text values. The taxonomy term pair that I mentioned before, each one of them is a again, the taxonomy is a coding system, and each term is a value in that coding system, and they're stored as text values. But what I did is I took a table and I created a dictionary of every combination of a taxonomy and term, and I inserted that into the table so that I would have a unique key value for it. And I had a big integer value, and that became my representation for that combination of taxonomy and term. And then I used that ID in all of my search criteria. I also had what's known as value sets. And in that, it's a collection of taxonomy term pairs that identify a given condition. So if I want to have a diagnosis of diabetes, this set of taxonomy term pairs could represent that. Now, I could have used the same text values and compared both values in this set to my data and did a lot of searching. That would work, wouldn't it? It would take a long time, but yes, it would work. But by switching it to a numeric value, it became much, much faster because my data set was smaller, and numbers are more easily searched than text values. Right? That's a noisy floor. And also, those value sets could be used for multiple measures. So I was able to get more bang for my buck in that way. Also, my primary data object was my element. This is what my tables were. And each element is known by a specific element type, such as a procedure or a diagnosis. And in those, we could also identify them by a taxonomy term pair as its characteristic. And each element can have 0 or more attributes. And all instances of that element, all of the records of the data themselves exist in the element pool. And each element instance, of course, is identified uniquely by its element pool ID. Our secondary data object is our attributes. And each attribute is known by a specific attribute type, such as what type of attribute that was. And the attribute could also then be identified by a taxonomy term pair. And each attribute can be used by more than one element type. So if I have an attribute of, say, date of birth, I may use that in multiple things. And each attribute instance was specific to a particular element instance. So I had a direct relationship between the two. For example, in my source data, I had the encounters, procedures, etc. And I loaded that with my definition of elements and attributes, into the element pool and attribute pool, and tied that in with my taxonomy term pairs. So as you can see, the relationships are beginning to get more complex. And on top of that, we have our value sets. And then we tied that in with our taxonomy term pair and created another table, which was my value set pair, which identified the unique numeric keys for this table and for all of those combinations. And then we paired that in with the element pool and attribute pool data. Now let's talk about queries. Use set-based queries. Anybody ever heard of Jeff Moden? He has great articles on SQL Server Central. Who reads SQL Server Central? Excellent, great resource. His coined phrase is rebar, row by agonizing row. That's what you do not want to do. So you want to avoid scalar-defined functions because they will break your set operations, turning your queries from set-based into like a row-by-row cursor. Use inline table value functions for the same reason, because you can use those to replace your scalar functions so that you do things in a set-based manner. Avoid cursors because they are not set-based. How many people have used a tally table? How many you know what that is? Using a table of numbers, you can do all sorts of things, replacing loops and replacing cursors with that. Very, very useful. Take a look on SQL Server Central for some articles on that. Now, there are a few times when you do have to use some loops, but I've kept them very, very few and for small iterations only. Windowing functions. Outstanding because they will be your best friend because they can help you to avoid loops and cursors as well. And they give you the characteristics of your group by without losing the detail in each of the records. You also want to avoid complex views because there is a tendency to have a view which references another view, which references another view. And a lot of developers think that's great modularization. But SQL Server can only handle so many nested views. And on top of that, I could have view A that has some computed columns, and then I reference that in view B. Well, in view B, I only reference the first few columns. I don't look at the computed columns. But every time I execute B, what happens to those computed columns? They get executed, right? So there's hidden things in there in those views, so be careful with that. You want to avoid complex queries if possible because of your memory constraints, especially with large data sets. It is actually more efficient at times to break your queries into manageable chunks, to have more sets of queries than one really large complex query. You want to take advantage of your set operators, union all, and intersect, and except. And you get a bonus out of that because when you do a union all, it encourages parallelism. If I have 5 select statements and I union them together and then do that into an insert statement, that is far more efficient than 5 different insert statements in the same table. Because those selects then get processed in parallel and the whole set gets combined for the insert. You can take OR conditions and break those up. If you have an OR in your where clause, ORs are not very nice to indexes because they make can break many indexes because they're not discrete enough. So if you take that OR condition and break it up into 2 different queries that are almost identical except for that where clause, and then union the results together, you get better performance usually. You want to avoid the use of distinct in your queries. This is something that gets overused so many times because they see duplicate rows, oh, let's just throw the distinct on it. What people don't realize is that you're having to do an implicit sort. So you're forcing the system to do things that it really shouldn't be doing. And it often covers up poorly written queries. So there was a reason those duplicate rows were returned. You could probably modify your query to avoid those duplicate rows. If you do have duplicates and you can't get around it, there are better options. Like, for example, using a row number function and getting those numbers and like calculating that in a CTE And then in your final result, you select all row number 1. That is far faster than doing a distinct. Table joins. You can rework your left joins into separate queries, especially if they're based on a condition. Query hints may be needed to encourage hash joins, but I put an emphasis on that they may. I'd be careful with that. I would suggest using avoid outer joins, because they can give you a poor performance on your table joins, especially on large tables, because you could be pulling in more data than you really want. Some people think that, well, I just pull all the data in, then I can filter it later. Well, that's a lot of processing that you don't need to do. You can often rework those with multiple queries union together. You want to avoid calculated fields in your join and where clauses. They could have some unintended side effects, because it could cause the queries to run in a row-by-row fashion. It could break your set base. It also causes additional calculations each time. So I'd suggest you either do that in a CTE or in another table, like a temp table, to do your calculation in that, and then query it. Yes?
Can you explain the left join part?
Yes, so when you're doing a left join, as you know, if I have table A, and then I'll left join table B, I'm going to get all the records from A and the rows from B where they match. Well, so there's, you're having to do that join right there. It might be better instead to say, I'm going to do an inner join from table A to B, take those records, and then query table A without table B. Now, that's not always the case. It depends on your data. So I should say your mileage may vary. So these are just things to keep in mind. Let's take a look at T-SQL. You want to use explicit transactions when possible. A lot of developers don't deal with them. They assume that, well, I'll have an implicit transaction for every query. But when you have a lot of queries, that's forcing the system to do a lot more work and overhead. If you have explicit transactions, even if you have them nested, instead of one big transaction, you can have your big transaction and then have smaller transactions within it. Then you help free up resources, because as you complete a transaction, system resources are returned, and so it frees them up for another transaction set. So that will help you on your performance as well. Store procedure calls. A lot of people, especially when they come from a .NET environment, they treat store procedures like they would .NET functions. And they have multiple calls, and they modularize their code. And I get why. It makes sense. But this isn't C#. It doesn't work the same way. In .NET, when you're going through all of those classes and modules and reused code, when you compile it, all of that gets worked out through the compiler. SQL Server, unfortunately, doesn't do that. And so you also want to minimize your complicated parameters. They can have an impact on your memory utilization. And same thing with minimizing the number and size of your output parameters, because that'll also tie up memory. Now, again, your mileage may vary. These are things that we discovered in our application. Your execution plans. They're very heavily dependent on your data volume. How many have had their queries run great in development, and they put it on production, and it stinks? Yeah, because what changed? The volume of data. So your execution plans, I can tell you this, it will change. Yes? Definition of a complicated parameter. Let's say that, here's one, value, or table value. Let me get that right. Table variables, thank you. All right, they're handy, but they can eat up some memory there. Or if you're having, say, 20 different parameters on a store procedure, you might want to store that data somewhere and have a simpler parameter set. that you then reference that data. Indexes. Now, I start out with partitions. Partitions aren't really part of indexes, but I kind of see them the same way because you're trying to organize your data. How many people are using partitions in your data? All right, quite a few. A great way to organize your data because it segments it into predefined units and predefined chunks. For example, when I took our element data, I broke that up by the element ID and I partitioned it so that when I had encounters, they were in their own partition. If you're on a on-premise solution, you can actually take that and put it into a separate file that could be on a different disk even. So that gives you a lot more flexibility. And it also helps you to keep track of things. So when you do an insert into, say, I'm inserting data into encounters, then I'm affecting only that file system right there and not everything else. So it makes it a lot more performance efficient. Yes?
We've got a SAN, and the TMC is pretty standard. And it's, my understanding is the most recently used data is in, SSD, and then when it's not used as much, it gets migrated to the slower disks. In that kind of an environment, I wonder if partitioning really helps.
That's a good question. So if you're using a SAN, does partitioning really help? Again, your mileage may vary. I found that it still helped us with what we had. Not so much necessarily for the, the disk management part of it, because let's say, for example, if you're lucky enough to have SSDs for your SAN, okay, then fragmentation really isn't that much of a problem. But the organization that partitions provide you do help quite a bit, especially even in searching the data. Yes? Right. And the other thing too is that with partitions, you can work it out so you can drop a partition without actually doing delete statements. And that's a lot faster. Yes?
Just elaborating more, like every partition has its own statistics histogram. So
Right. The statistics associated with partitions help too. Yep. No problem. A proper use of indexes. Use covering indexes where appropriate. That doesn't mean that you want to throw out every index possible. I have seen a rather small table that had more indexes on it than it had columns of data. And why? Yes?
Which version of SQL Server was this on?
This was on 2008. Yeah. Yeah, the reason why is because, somebody took a query, they thought, well, maybe this is a problem, put it in the query analyzer, and it said, oh, you need this index. Well, let's go throw it in there. And, they just kept throwing out whatever index it said it needed to have, and next thing you know, you've got, 24 indexes that are basically the same thing. What I do is I take a look at the joins, query joins and where clauses, and I base my indexes on those. You want to have plans to periodically reevaluate your indexes. Take a look at them. See which ones are being utilized. If you have indexes that are not being utilized, get rid of them. Because every time you add data to the table, what happens? It has to go and update all of those indexes as well. I also used work tables that were just straight tables, didn't have any foreign keys, didn't have any indexes on them because they were expected to be small data sets. And so that also helped performance. I use those instead of, at times, temp tables because I could manage them better, especially when I was creating them all the time. So I just created a static work table. Now you're probably wondering, after we go through all this exercise, what other alternatives could we have done? Well, as was already asked, we were on SQL Server 2008 at the time. So could we have used column store indexes? That's kind of a cool idea, column store index. How many people are using column store indexes? Okay, a few. They're pretty handy, but they're not for everything. One of the things is that, they didn't exist for 2008, and they don't preserve the relationship between the columns. Yes, you can look up the data much, much faster, but if you're wanting to say, I want that and some other associated data, then it's more of a problem. I did take a page from the column store index book, and I did a deduplication of results. So that really helped with performance, because when you're processing the same clinical quality measures every day, and you're doing it for multiple time frames every day, a lot of the results are going to end up being the same. And so I stored the results only once, calculated a hash value for those results, and if I had already stored the results from my working area into the analytics side, then I didn't store it again. I just stored a pointer to it. So it became much easier to operate. Yes?
The second point about it is not to change the relationship between columns. Are you just talking about primary keys and points?
Yes. Right.
We made improvements.
Yes, and again, this was done before 2016, I should say. So keep that in mind. This was back on 2008. Could we have used another platform? Could we have used Hadoop instead? Well, Hadoop, the data that we have is highly relational, and it requires updates and deletes, so Hadoop wasn't an option for us. Massively parallel processing system. We did do a port to Netezza, and it worked well. We had some hurdles to jump through that, but we could have done it on Teradata as well had we had the need for it. It would have worked well. Could we have used multiple SQL Server instances? We could have replicated the data, and that way we could have a measure running on different servers at the same time against the replicated data, and then we could combine the results. But when we looked into that option, we figured it was going to be more hassle to stitching everything back together, and so we decided not to do that. So let me go over some closing thoughts for you here. SQL Server, or the NoSQL big data environments. It relies upon sharding and parallelism for its performance. That's what gives Hadoop its big gain, is that you have so many servers working on the data at the same time. But it has some unique data considerations. The fact that it is intended to store and fetch data. That's its primary purpose, and it does a bang-up job on that. But it's not built for updates and deletes. It's not meant to be a relational database. And it's very effective on non-discrete or unstructured data. But there is no built-in query tool or language. Yes, there is Hive SQL. There are things you can add to it. But it's not built into the system. All of its processing is done outside of the database. But it does allow for some pretty complex programming and for some pretty cool algorithms. That's why it's very, very popular for some of those analysis, especially math-based analysis. And you also have a wide range of tools to look into that, such as Python or R or many other languages. But again, it's not a relational database engine. The SQL interface that's put there is for convenience. It's for, if you want to do something occasionally or to, look at some data. But it's not meant for a productionized version. The tools are improving, but it still needs a lot of work before I would consider it to be effective for relational databases. SQL Server, on the other hand, it's a true relational database engine. It's designed to perform updates and deletes. And it has better performance when using set-based logic. It works well with structured data. Again, but it has to be structured when you load the data. But it doesn't matter if it's a high volume of data. It can work with multiple terabytes of data. But I would say that it requires proper architecture and tuning. You don't want to just throw it in there and expect it to work. I would take a look at your data movement operations, like in your ETL operations or things where you're moving data from one place to another. Make sure you're not doing anything that you don't have to be doing, because otherwise you'd be wasting resources. T-SQL performs, of course, the data processing, and is very close to the data. That's one of the advantages that SQL Server has in its performance over something like Hadoop, because in Hadoop, you have to have the application go and do something with the data, bring it in, and there's a lot of passing back and forth. Whereas T-SQL operates right on the data, and so it doesn't have to shuffle it around. Unfortunately, SQL Server is limited to a single server. But remember that Azure is basically multiple SQL servers, multiple parallel processing SQL servers in the cloud. So keep that in mind. Do you have any questions? Yes?
I wanted to comment from my reading of the theory of Hadoop. Their goal is to divide the data out so that on each node, they do all the data processing and only return a small data answer back to that set. So they're not comparing across multiple nodes.
Right.
Really. So in that scenario, it seems to make sense. But yeah, my understanding of Hadoop is it's a specific use case. It's not a global tool.
That's true. And that what you're referring to there is similar to what is done with massively parallel processing systems, where they try to do like joins, et cetera, on data at the node level so that it doesn't have to transfer all that data back through the wire to the main controller for it to be processed. That is true. Yes?
What went into the decision to not go with like a star schema or a traditional data model?
Good question. Why didn't we use a star schema or something of that nature? Because it really wasn't a data warehouse in the sense of a traditional data warehouse. And in traditional data warehousing, you do a lot of, denormalization, for efficiency, but it also increases the volume of your data. And because of the size of the data that we had, we didn't want to do that because then it would just added even more load to the system. So we did a hybrid, really, between a transactional and a data warehouse type setup. Yes, ma'am?
To follow up on that then, did you use any kind of industry standard modeling or something in between everything?
It's funny you should ask what modeling method I used. I developed my own, and then afterwards I found that there were several other solutions that were out there that were kind of similar to what I did. And so, I reinvented the same thing that others already did. It was like when I did the original data source, somebody said, oh yeah, that looks like OMOP. And I was like, what's OMOP? And it has to do with some data model that was used to represent clinical data. And it's like, well, similar problems end up with similar results, right? With similar solutions. Yes?
Have you used the XML column store, storing XML inside columns in SQL Server, and how does that perform?
For storing XML within columns in the database, I did that as far as the measures were concerned. When we compiled the measure into a store procedure, I stored the original measure definition in an XML column, but that's all I did with it. I did that because if there was a question as to why was something done and the measure had changed from the outside, I wanted to know what that original was at the time when I compiled it. Yes, sir?
Well, excuse my lack of experience, but I guess I don't know what that means by taking an XML document and compiling it.
Yeah, I should clarify. The compiler that I used for that was one that I designed as well. So I worked with a .NET developer, and I gave him the logic of what I wanted as a transformation from an XML into T-SQL code. And so then he processed that. So he would take that, read the XML in, and process it into a file that was a store procedure. Yes?
Referring to your early part of your talk, when it comes to vendors going directly to the business or directly to the C-level suite, shiny.
Yes.
What's the antidote to that? I mean, you're preaching to the choir.
That is true. It really, I hate to say this, but sometimes you have to, give counter evidence to that. Because in those C-level magazines, that's where they target those type of articles. And whatever the tool may be, whatever the new shiny thing is. So you have to give them a dose of reality. And you really need to have a working relationship with management so that they say, hey, you know what, I found this, what is your opinion of it? And then you can give them that taste of reality. Yes?
Microsoft has an army of C-level projects, so they have the higher levels, so they can.
Yeah, so you can always use the Microsoft goons against them, you know. Yes? Can't say that I've used distributed partitions. So, sorry. I'd love to tell you about it, but haven't had the opportunity. If you get the slides, there's also, in addition to the links for all of the references that I made, the articles, I do also have some links for free ebooks from Microsoft, Redgate, and SentryOne. Again, the presentation feedback, I would really, really appreciate that feedback. Write some notes in that if you could to let me know what I need to do better on or what I did well so that I can continue doing it. I do have my contact information there as well. If you have any questions, I also have some cards up here if you want to talk further about it. It was a really, really neat project that I worked on, and I learned a lot from it. It's always great to have those type of projects that cause you to learn and grow. But the best thing to do is once you learn and grow, you want to share that with others so that they can also learn and grow. Thank you very much. Appreciate it.